Welcome back to the continuation of Lecture 7, in which we are talking about solutions to second-order constant coefficient linear differential equations. We already talked about the fact that the general solution to an ODE with no damping can be expressed either in terms of a linear combination of complex exponentials or in terms of a linear combination of sine and cosine. And that is because both the complex exponentials and the sine and cosine are basis functions for the solution space. Let's get to an example. If we consider the initial value problem y double prime plus 49y equals 0, with initial y value at 1 and the initial derivative to be 0, we can actually solve this ODE in two different ways. One using the complex exponential basis and one using the sine cosine basis. What I would like you to do is pause the video and challenge yourself to try to solve this one ODE with the two approaches. First, we know immediately that in both cases, the characteristic equation has the form lambda squared plus 49 is 0, which has roots plus or minus 7i. Therefore, the basis functions in the complex exponential case are going to be e to the 7it and e to the minus 7it, whereas the basis functions in the sine cosine case are going to be cosine 7t and sine 7t. Solving the initial value problem in the case of the complex exponential, we know that the function y is a linear combination of e to the I 7t and e to the minus I 7t. Plugging in initial conditions, we know that y of 0 has to be c1 plus c2, and y of 0 is 1. And then we have to compute what the derivative of our solution y is before we plug in the initial condition. And in this case, it's going to be c1 I7 e to the I7t minus c2 I7 e to the minus I7t, which means when we plug in the 0 time value, we get 7i c1 minus 7i c2 equals 0. Putting these two equations together, we know that c1 minus c2 is 0, and that c1 plus c2 is 1. Solving tells us that c1 therefore has to be 1/2 and c2 has to be 1/2. Writing our solution to our initial value problem, then we get that y is 1/2 e to the 7it plus 1/2 e to the minus 7it. And this solution satisfies both the ODE and the initial conditions. Now, doing the same thing but using the basis cosine and sine, we then write our general solution is going to look like a constant times cosine 7t plus another constant times sine 7t. Plugging in the initial conditions, we have that y at time 0 is constant a plus 0. That has to be 1, which means that constant a has to be 1. Now let's take the derivative of our solution before we plug in our second initial condition, and we get minus 7a sine 7t plus 7b cosine 7t is y prime. Now we can plug in times 0 to y prime, and what we get is 0 plus 7b equals 0, which of course means that b has to be 0. That therefore yields the fact that our solution to the initial value problem becomes cosine 7t. It looks like we came up with two different solutions, but in fact, these two solutions are identical via Euler's formula, where cosine theta equals e to the I theta plus e to the minus I theta over 2. Whether or not you use the complex exponential basis or the sine cosine basis is up to you, unless of course you're asked specifically to use one or the other. Let's go to the next page and look at what happens when we add back damping. Here now we have an ODE in which we've turned damping back on. So our damping constant B is not going to be 0 anymore. The general solution to our second order linear constant coefficient homogeneous ODE can be described this way. If the coefficients A, B, and C are real, the roots of the characteristic equation are going to be complex if B squared minus 4AC is negative. The two roots are minus B over 2A plus minus I times square root 4AC minus B squared over 2A. If we define sigma to be minus B over 2A and omega to be root 4AC minus B squared over 2A, then we can rewrite the solution as sigma plus I omega. This is a useful reminder that the roots of a characteristic polynomial are always going to come in complex conjugate pairs. Using this formulation, two linearly independent solutions then are given by e to the lambda 1t, which is written as e to the sigma plus I omega t, and e to the lambda 2t, written as e to the sigma minus I omega t. But as we've done before, instead of using complex exponentials, we can also use sine cosine via Euler's formula. So here are two other linearly independent solutions. Let's take a linear combination of y1 plus y2 and divide it by 2, and we end up with e to the sigma t cosine omega t. And let's take y1 minus y2 and divide it by 2i, and we end up with e to the sigma t sine omega t. So now we see that the general solution can be expressed in one of two ways, with complex exponentials or with a sine and cosine. The difference between what we're seeing now and what we saw on the previous page is that we have a damping term. How does that damping term come into play here? It's showing up here in the e to the sigma t term. Otherwise, the complex exponential versus the sine cosine formulation is the same as what we saw on the previous page when there was no damping. Again, each representation shows how the solution space is spanned by a basis of linearly independent solutions. Let's go to the next page to see how this is summarized. Overall then, if we're dealing with a second order, linear, unforced, constant coefficient differential equation, we will have a characteristic equation of this form, a lambda squared plus b lambda plus c equals 0, and its roots will always be the roots of a quadratic. Now, the cases we have are the following. Either we have distinct roots, where lambda 1 is not equal to lambda 2, and the solution will take the form e to the lambda 1 and e to the lambda 2 in linear combination. If, on the other hand, we have a solution where lambda 1 equals lambda 2, recall that to get two linearly independent basis functions, we now need to have an additional factor of t in our second basis function. So we have a linear combination of e to the lambda 1t and t e to the lambda 1t. Now, this isn't exactly a third case. It's just a way of rethinking the first case. An alternate way of thinking of the solution, if lambda 1 and lambda 2 are not equal, but are complex conjugates of each other, is to then write the solution in terms of a cosine and a sine. At this point, you have a chance to try some of this yourself. Now, had we been there in person, you would be working in groups. If you wish to work in groups still, feel free to work on this problem together and submit your work on Canvas as usual. Or if you want to work on your own, you can do that too. These are the steps you're going to follow. You're going to write the general functional form for the solution of the ODE that you're given. You will write down the associated characteristic equation for the unknown lambda. Of course, we're going to find the roots of the characteristic equation and then use those roots to write the general form for the solution. This general form is going to include constants, C1 and C2 say. Then we can pin those constants down by using the initial conditions. Finally, sketch a solution curve on the TY plane, just a general shape. It does not have to be precise. And do take a screenshot of your work to turn in on Canvas. The two examples are as follows, and they are also available on the Lucid Spark whiteboard if you wish to work there. Otherwise, you can work on your own scratch paper or tablet and turn in. Take some time and complete these problems now, and then I will show you how I would complete them. Using our characteristic equation, we find the roots and the general solution, which in this case is e to the minus t, c1 cosine t plus c2 sine t. The initial conditions then are our final step. Y of 0 is c1, which we have set as 0. And then, of course, to find y prime, we first take the derivative of our solution, but I've already plugged in the fact that c1 is 0. Y prime of t is therefore c2 e to the minus t cosine t minus sine t. At 0 then, y prime is c2, which we have said is 2. Our solution therefore to the initial value problem is 2e to the minus t sine t. And in the ty plane, that'll look something like this. A bump up, a small bump down, and then it tends toward 0. Why is it tending toward 0? Because we have the e to the minus t term, which as t goes to infinity, sends the entire solution toward 0. In example 3, we do something similar. When y of t is e to the lambda t, the characteristic equation becomes lambda squared plus lambda plus 1 equals 0, which has complex roots, minus 1/2 plus minus I over 2 root 3. The general solution is therefore y of t is e to the minus t over 2 times a constant cosine root 3 over 2t plus another constant sine root 3 over 2t. Using the initial conditions then, we can find y of 0 right away. That's going to be c1, which is 1. Y prime of 0 is going to be c2 root 3 over 2 minus 1/2. That's equal to 0, which implies that c2 has to be 1 over root 3. The solution to our initial value problem, therefore, is e to the minus t over 2 cosine root 3 over 2t plus 1 over root 3, which is our c2, sine root 3 over 2t. Using trigonometric identities, we can actually also write this as a shifted sign. Make sure you feel comfortable with this solution process when you try it yourself. Finally, let me find some room to sketch this here. The sketch of this solution looks very much like the previous one. We have a little bump down, a little bump up, and then comes back down to 0. Let's look at a summary of what we've done on the next page. In the case of a mass spring system, when it is damped but unforced, We'll always have a differential equation that looks like this, where the coefficients m, c, and k are positive or zero. The roots of the characteristic polynomial are always going to have the form minus c plus minus square root of c squared minus 4mk over 2m. Now, if m, c, and k are real and non-negative, there are three different types of solutions based on the value of the discriminant c squared minus 4mk. In particular, if the discriminant is strictly positive, we have real distinct roots. This is considered an example of overdamped motion. In other words, you can have an initial bounce and then the motion gets damped away immediately. In the case the discriminant is 0, then we have repeated roots. This is an example of what is called critically damped motion. It looks similar, but it essentially represents a damping that goes as fast as possible before becoming oscillatory. And then finally, once the discriminant jumps over to becoming negative, we get complex roots. And that gives us underdamped motion. The oscillatory component comes from the sine cosine, and the damping comes from the e to the sigma t term. So all these cases are from one ordinary differential equation, and how the solution behaves depends on the coefficients of the ODE. Let's look at how this translates into standard engineering notation on the next page. Instead of talking about damping in terms of the coefficient c, we're going to do a little bit of a translation so that we can make use of something called the damping factor zeta. So we are using the MKS units. We're going to divide our standard equation by m, putting it into normal form. And as before, we're going to define omega squared to be k over m. Omega is, of course, the natural frequency. What are the units? Radians per second. That yields for us the canonical oscillator equation. Now we're going to define our term zeta to be c over 2 root mk, so that c over m is 2 zeta omega n. What now are the units of zeta? There's a reason zeta is written this way. Zeta has now become dimensionless. It is our dimensionless damping factor. So now we can write our oscillator equation in terms of zeta as follows. X double prime plus 2 zeta omega x prime plus omega squared x is 0. So as we pointed out, zeta is called our damping factor, and it is dimensionless. Dimensionless parameters are useful because the actual quantities of the damping don't matter quite as much as the sign of the damping factor to tell us something about the overall behavior of the solution. Now, in this case, we can look at the roots of the characteristic equation table one more time, but this time in terms of zeta. Now the type of solution depends on zeta alone. If zeta is greater than 1, we have real distinct roots and again have overdamped motion. If zeta is equal to 1, we get repeated roots and critically damped motion. But now, if zeta is between 0 and 1, we get complex roots and underdamped motion. And if zeta is 0, we have no damping at all. This still falls into the category of underdamped motion. The underdamped motion means that the oscillations are going to continue forever and ever, and the amplitude of the oscillations is not going to diminish over time. Okay, that's it for lesson 7. See you in lesson 8.